So I'll move on. I'll move on to more classical random graphs where the randomness is in the edges. And the general framework that we look at is the following. Consider there are two distributions on the space of all large graphs that we can have. By large, I mean all graphs that have at least n vertices. And what we see are two graphs, one generated from each of these distributions. And after observing these two graphs, we want to test whether the two large graphs come from the same model or they come from models that are separated by some distance rho. I will specify what is this metric later. In fact, we will work with a weaker metric. And the objective is to find a good test in the sense that in the worst case, that is for any given pair of models, the probability of falsely rejecting or accepting any hypothesis would go down to 0 as the minimum graph size grows to infinity, n goes to infinity. Note that this is different from standard learning or testing scenario where we have multiple samples and we can talk about sample complexity. Here we observe only one graph from each distribution. And so in general, this problem would be unsolvable. So the main question is, when is this problem solvable? Well, this particular problem has been there in the literature in special cases for quite some time. In theory, I mean, you may want to look at whether a random graph has some communities or whether it has a geometric structure. And in practice, you may want to see whether two brain networks are same or not. And one of the principal approaches in dealing with graphs is that you compute some network function from the graph, say the degree distribution or the number of triangles, and then you compare graphs based on that. You don't compare the graphs directly. You cannot compare the graphs directly. In theory, it makes perfect sense. So if you want to test whether the network has a community, you would want to see the Laplacian eigenvalues or the modularity, and that would reveal whether it has communities or not. But in practice, when people say, well, Alzheimer's reduces the small world properties of brain networks, it's a vague statement. So formally, what is the kind of questions that people actually solve in practice when they talk about comparing between two large graphs? And the second question that we are interested in, rather the third, because the first question is when this problem is actually solvable. So the third question is the techniques that we use in theory, how much can we extend them? Those techniques are, I mean, tuned for very specific distributions, like when you deal with Erdős-Rényi or block models, you use these techniques. How much can we extend these results? And well, this paper is not a paper with very cool technical results, but it's more of a paper which sets up a framework where now you can put everything and plug and play. We don't prove any new results in the sense that whatever we say are mainly derived from theoretical results already known. But now we create this plug and play framework that one can really use, even people in practice can also use. So the first observation is that, well, we wanted to compare between these two models, but we don't compare the graphs, we push it to another metric space and then do the comparison. So we are basically losing some information, and we cannot distinguish between the models when they behave in the same way in this final metric space. So let's just try to formalize this simple observation. And the main fact is that we will work with a weaker metric. We'll test across a weaker metric. And when can we actually pose the problem in this large graph, one sample scenario? Well, here's one set of sufficient conditions. You assume that there is a subclass of distributions such that whenever you pick a guy P from here, there exists a mapping of P to the final metric space, let's call it MP, such that whenever you draw a sample from this distribution and then compute the network function on that, F is that network function that underlies the whole problem. You want to test with respect to degree distribution or something. So condition is that F should concentrate around MP. That is, with high probability, F should lie in a ball around MP with radius sigma p. And then we state the obvious problem. For any pair of models, we are basically testing whether their projections MP and MQ are same or they are separated by some distance. I mean, till now it's very intuitive. This is what we actually should expect. But the interesting fact is that the moment you pose the problem in this way, there exists a very natural test which is even uniformly consistent. You just compute the distance between the two network function values computed on the two graphs and then test it with respect to some threshold. And one can show that this test is uniformly consistent. That is, whenever you get graphs from this subclass of distributions, the error rate will go down to 0 as n tends to infinity, provided that this minimum separation rho grows faster than the noise level. So this is the rho that we had here. It grows faster than the noise level. And the proof is obvious. Basically, we are ensuring with this condition that the two balls are separated enough. And fun fact, this test is sometimes even minimax optimal. Because, I mean, this is again based on results that are already known in theory. If your graph, your class of distributions is large enough so as to contain the stochastic block model and the Erdős-Rényi, then we already know that there is a detection threshold between these two models. Below that level, you cannot distinguish between these two models. And, well, all you need to do is translate all those facts with respect to the function that you're now considering. And which gives you the result that, well, if the separation is below the noise level, no test can solve the problem. Whereas above the noise level, this generic test can. And that's the whole message of this paper, that whatever we already know in theory doesn't apply to very specific model classes, but you can start comparing graphs, very large graphs, even when you have one sample, as long as you pose the problem in a neat way. And, well, this immediately motivates one to study what other network functions would concentrate, like whether we can look at things like centrality measures or betweenness stuff and clustering coefficient. Whenever you prove a concentration for that, you can test two graphs based on that. And well, I'll end with a note that, as I said, this is not a paper with cool new results. If you really want cool new results related to graph testing, you should look at this archive paper that the same four of us wrote, which was actually the motivating paper for this. We started with this work, and this COLT paper is rather a byproduct of whatever we learned there. There we test try to compare graphs defined on the same set of vertices, and we get near optimal test and minimax rates for testing such cases. Thank you.
All right, are there any questions? All right, so I guess we'll take a coffee break. What time should we come back? 10 minutes. In 10 minutes, coffee break. Let's thank the speaker and the speakers of the session.